We'll now continue section 5.5, discussing exponential and logarithmic equations. We're going to look at applications of these particular equations in this presentation. So we'll begin with an application involving compounding interest. Rita is saving up money for a down payment on a new car. She currently has $5,500, but she knows she can get a loan at a lower interest rate if she can put down $6,000. If she invests her $5,500 in a money market account that earns an annual interest rate of 4.8% compounded monthly, how long will it take her to accumulate the $6,000? So remember that we have a formula for interest that is compounded monthly. Remember that that formula looks like A is equal to P times 1 plus R over N raised to the N times T power. And so we simply need to look at our numbers and determine what's going to go where and set it up. So we have our interest rate of 4.8%. So we know that the R is going to be 0.048. We know that it compounds monthly, so that's going to be the N value. Remember, N is the number of times it compounds a year. We know that her final amount that she wants is $6,000. And her initial amount is $5,500. And we're looking for the T because it's asking us how long will it take her to accumulate the $6,000. So let's go ahead and plug these numbers into the formula and then look at solving the formula. So we're going to have 6,000 is equal to 5,500, 1 plus 0.048 over 12 raised to the 12 times t. Now, in an example like this, where we are solving for an exponent in an exponential equation, we can employ some of the techniques that we've learned in this section. So our goal is to get the t by itself, and so we're going to begin by dividing by the 5,500. And while I could simplify this, for now I'm just going to leave it be. So I'm going to leave it as 6,000 over 5,500 is equal to, and in parentheses I have 1 plus 0.048 over 12 raised to the 12t. Now, somehow we need to get that exponent down and make it a regular number and not an exponent. And the only way I can pull that exponent down is to have a log involved. And so I'm going to take the log of both sides of the equation. You can either use the common log or you can use the natural log. It does not make any difference. I'm going to use the natural log here. And so I'm going to take the natural log of this 6,000 over 5,500. And I'm going to take the natural log of 1 plus 0.048 over 12 raised to the 12t. And once I do that, then I can take this 12t and move it to the front. Okay, so let's work on this a little bit. I am going to go ahead and I'm going to leave the left-hand side alone. And the reason that I'm not dividing the 6,000 by the 5,500 is that when I do that, I end up with this lengthy decimal. So I'm trying to avoid the rounding that I would have to do there. But on the other side, if I calculate what's inside this parenthesis, I don't get a long decimal. So I'm going to go ahead and do that. and I get 1.004. And we are moving that 12t down to the front, so let me do that as well. Okay, and then we need to divide. So we're going to divide by everything that's not a t over here. So we're going to divide by 12, and we're going to divide by the natural log of 1.004. All right, and so we're going to plug this expression into our calculator, the natural log of 6,000 divided by 5,500 divided by 12 times the natural log of 1.004. And when we do that, if you enter it incorrectly, and as always you can email me and ask if you're not sure, we're going to come up with 1.82. This is in terms of years, and so what that basically means is 1 complete year and 0.82 of a year. And so we could do 0.82 times 12, because there are 12 months in a year, and that tells us that it's roughly about 10 months. Okay, and so we're talking about it taking a year and 10 months in order for her money to accumulate to the 6,000. And this is an approximation, 1 year and 10 months. Okay, so let's move on to our next example. Our next example involves radiocarbon dating, or half-life. So we've already discussed how the radioactive decay of carbon-14 can be used to arrive at age estimates of carbon-based fossils, and we constructed an exponential function describing the rate of decay. So our function looks like a of t is equal to a sub 0 times e raised to the negative 0.000121 t. A sub t is the mass excuse me, a sub t is the mass remaining after t years. A sub 0 is the mass that you had initially. And so we want to use this formula to determine, first of all, the half-life of carbon-14. All right, so I am going to start for part A, and I'm going to write that formula down that we were given. So A sub t is equal to a sub 0 e to the negative 0.0000121 t. Okay, so remember that a sub 0 is our initial value, a sub t is our final value, and we want to determine half-life. So the way that we worked this before is that we came up with a set of numbers that preserve the relationship of half-life. So we said we could use whatever we wanted as long as one of those numbers was half the other one. All right, so in other words, the a sub 0 is your initial amount. So you can pick something here for that initial amount. Let's pick 1,000. And so your final amount is the a sub t. And if we're talking about half-life, then that is going to be half of the 1,000, so 500. And it doesn't make any difference what you select there as long as your a sub t is half of your a sub 0. All right, so let's plug in. Let's see what we've got. So I'm going to plug in a 500 for the a sub t, a 1,000 for the a sub 0, and I am going to solve it for t, because remember we want the half-life. We want to know how long is it going to take. All right, so first thing I'm going to do, I'm solving for t, is I'm going to divide by 1,000. And so 500 divided by 1,000 is a half. And the 1,000s cancel on the right, and so we're just left with the e, and we've got our decimal exponent. All right, now again, we want to bring that exponent down, and the only way that we can bring the exponent down is if we involve the log. And so you can do a common log or you can do a natural log. I'm going to do a natural log of both sides. So I'm going to do the natural log of 1/2 and the natural log of e to this decimal exponent times t. Now, once that's done, then this exponent can come down to the front. Okay, and if you'll check, if you don't know already, you can check, but the natural log of e is equal to 1. So you could type that in your calculator and see that that's the case if you're not familiar enough yet to realize that. But that is going to actually just kind of fall away because it is equal to 1. And so we have the natural log of 1/2 is equal to negative 0.000121 t. And again, we want to solve for t, so we're going to divide by that decimal. Causing it to cancel on the right, and that solves it for t. And so t is going to equal 5728 years. And so that's going to be the half-life that we were asked to find. Okay, so for part B, it asks us to the age of a fossilized organism containing 1.5 grams of carbon-14, given that a living organism of the same size contains 2.3 grams of carbon-14. Okay, so let's take our formula that we have. So remember our formula was a sub t is equal to a sub 0 times e, and then we had that decimal exponent times t. Now this time we know what the t is, and we know what happens for the half-life. So we're going to plug our information in, and we're going to solve for t. We want to know how long does it take for this organism to reach this point. All right, so let's look at the information that we have. So the fossilized organism contains 1.5 grams. The living organism contains 2.3 grams. So originally it had 2.3. The final value is 1.5. So I'm going to plug in 1.5 for the A and 2.3 for the a sub 0. And again, we're solving for t. So the only way that we're going to be able to solve for t is if we can get that exponent down. The only way you can get the exponent down is to take the natural log of both sides. So I'm going to take the natural log of 1.5 and the natural log of 2.3 e. Well, I'll take that back just a second. What do we need to do first here? We need to divide both sides by 2.3. So I skipped that step by accident. Let's get that in there. All right, so I'm dividing by 2.3. I'm going to leave this fraction as is. So 1.5 divided by 2.3 is equal to e to our decimal times t. All right, so again, we want that exponent down, so we're going to take the natural log of both sides of the expression. So I'm going to have the natural log of my fraction, and we're going to have the natural log of e to our decimal exponent times t. All right, that's going to allow us to now pull that exponent down to the front. So this is working just like part A in terms of what we have to do. remember that this natural log of e is equal to 1, so it kind of just falls out. So we have the natural log of 1.5 divided by 2.3 is equal to negative 0.000121t. Okay, and then finally we're solving for t, so we're going to divide both sides by that decimal. Causing it to cancel on the right. And we're going to plug in what we're left with into our calculator. And so you should get 3,533 for your t value. And that is in terms of years.